Okay, thanks everyone for making it to the very last session. There's a picture here showing on the background, and it's one of my favorite paintings. If you ever come to London, you can see it at the Tate, and this is a picture by William Blake. It's called Newton. And the image celebrates Newton as a scientist, his focus, his rigor, how dedicated he was towards mathematics and various parts of science. At the same time, this image is a criticism of Newton. Newton's back is always facing the natural world. He was never really interested in other parts outside of the world that he was focused in. And so that's why I'm really excited to be here today so that we can talk about sort of the convergence of different areas of science, of Bayesian reasoning, of deep learning, a bit of reinforcement learning, and see how these things come together. It's one of the things I'm really interested in. And so we'll have that bit of discussion, and we'll think about reasoning systems and what I'll call Bayesian agents. So if it goes to the first slide, let me put it on. Okay, so let me summarize what deep learning is, and you've heard all these things today. Deep learning for me is a framework for constructing very flexible models. And there are a number of properties of these kind of flexible models that we have. They give you rich, nonlinear models for classification and sequence prediction. The second point, they are scalable learning using stochastic approximations. Conceptually very simple. We all know how to build them together. We can easily compose anything from deep learning with other gradient-based methods. But there are some disadvantages. For example, you only often deal with point estimates when you do deep learning. And it's hard to actually score these models correctly, do model selection, evaluate their complexity, and then do penalization in these ways. On the other hand, you have the other part of this workshop, which is Bayesian reasoning. And for me, Bayesian reasoning gives you a framework for inference and decision-making. And these two terms will be sort of what we'll talk about for the rest of the time. And again, we have a number of advantages. We have a unified framework for model building, inference, prediction, and decision-making. We have explicit accounting for uncertainty and any variability in the outcomes. We are robust to overfitting of the model. We can do selection and we can do composition. But Bayesian reasoning itself has limitations. For the most part, you see conjugate and linear models to make things efficient. And if you don't do that, you are faced with the problem of intractable inference. So you're leading to expensive computation, long simulation times. So when you put these two things together, you get two of the most active areas of machine learning today. You get deep learning and Bayesian reasoning. The advantages of the one are actually the disadvantages of the other. So it is natural to actually marry these two approaches together, and hence everything we've seen in this workshop today. So I want to just begin with this framework of inference and decision-making. And here I'm going to take the inspiration from the book of E.T. Jaynes. There are two distinct processes that we have to do when we're trying to build a system that does reasoning, like an agent in an AI, for example. You have the process of what you can know about your data, and this is what we call inference, and in this case we'll call it Bayesian inference. But inference that's all inference tells you, what you can know about your data. The other thing that you'll see is what you can do with your data, right? And then this is the part of decision-making and risk analysis. And for this part, let's consider Bayesian reinforcement learning or any kind of decision-making in general. So if we look at everything we've discussed today and throughout NIPS this year and all the other workshops, we have all the ingredients that we need to build a reasoning system. So we have a flexible way of building models using deep learning. We have the ability to make consistent inference and maintain our beliefs using all the tools of approximate Bayesian inference that we spoke about throughout the conference. And then we can reason about potential outcomes and take decisions together. So basically, we can try and think about ways of putting these two things together. So a little bit of tour about sort of probabilistic epistemology. There are two types of models that I think about these days, or two ways that I classify models. One of these ways are what I call prescribed probabilistic models. And these are models where you actually specify an entire joint probability, giving you a likelihood function that helps you score the probability. And the likelihood function is great because if you believe in the likelihood principle, this will work. And the likelihood helps you avoid many pathologies of dealing with data and support. And for example, variational inference, which is a theme throughout the conference, is one way that falls as a natural solution to these class of problems. Maybe a more fundamental class of models are called implicit probabilistic models. They just define a stochastic data generating mechanism, and then we need to ask what is the principle of inference in these class of models, and we'll have a quick look at hypothesis testing as the inferential principle. So these are the two types of models in general that we have available to build a reasoning system, and we'll build these models using deep learning. So the pragmatic Bayesians amongst us recognize that we want to use probability as often and as much as we can because it helps us represent our beliefs. But there is a spectrum of ways of doing estimation that we live on. And we have to make a decision about where on that spectrum we want to lie. And so one of the main spectrums that we've been thinking about is point estimation on one end that we typically do with deep learning, and on the other end, the full posterior distribution. And we will often want to be in the middle, and we want to constrain ourselves against some other kind of criteria, and typically these are computation and memory. And we'll try to find the solution that helps fit in that space. So the first way of doing inference is what I will call the default statistical method. And this is the thing I think should be the default method for statistical inference. And that is to use variational inference as the way of dealing with probabilistic models, especially for prescribed probabilistic models. And so the problem of variational inference is to find and solve for this posterior distribution that we always want within some restricted class of probabilities. We've seen this famous variational free energy objective that is, many people have spoken about, that gives us a unified objective function that is principled and allows us to include the properties of Occam's razor that we heard about earlier, as well as data fidelity. And using this framework these days, we have a very modular, very simple way of thinking about it. You could call them the variational building blocks after one of the papers that I like named that way. And you just need to, even in your code and in the way you think about models and inference, build these composable blocks. There is a model block. You implement it in TensorFlow this way. There is a prior block that needs to be sampled and evaluate the log probability. There is an inference block, and then you just need to stitch them together and sum, and then that gives you a loss. So this approach gives you everything that you need to be composable, easily fits in with the rest of deep learning, other kinds of gradient-based methods. Everything we know about other ways of doing probabilistic modeling can fit into this sort of building blocks approach. And if you ever hear people telling you that variational inference is limited in some way, that is because of the choice of this Q. But today we have very highly flexible ways of choosing this Q distribution, which means this is not so much of a limitation. So typically, this is the way we will deal with things. The other end is another class of models that are increasingly popular everywhere, and these are these implicit generative models or implicit probabilistic models. And whereas in the previous case, we looked at the marginal likelihood as the principle of inference, now you need to ask what is the principle of inference that you will use when you have just a simulator of your data. And in this case, the principle of inference will be about two-sample testing or hypothesis testing, or in general, just ways in which you can compare data. And so this you will call in general a principle of density estimation by comparison. And density estimation by comparison always involves two steps. It involves first a comparison step where you have two samples of data and you make a statement about how related these two samples of data are. And once you have an object that tells you how related they are, you then can do an estimation of your model. And then that is the estimation step. And this has many names in machine learning and various other areas. Density estimation by comparison is one I like. Indirect inference is another one that I like quite a lot. And if you're doing unsupervised learning, then you could call this unsupervised learning as supervised learning, for example, for someone. And there are many ways of dealing with this. So again, that spectrum exists. On the point estimation side, you have things like generative adversarial networks that you heard about earlier, or what we have the generalized simulated method of moments on one end, or if you want to be Bayesian and fully Bayesian on the other end, you you have what is called the classifier ABC method, or even more newer methods like ABC, MCMC. And again, you have to choose as a pragmatic Bayesian what kind of approach you want to use, how much computation you can give, and what your task actually is. And we'll try to be as Bayesian as possible, but within some constraints. So these are the two ways of building models and thinking about inference. The other part that I said is that tells you what you can know about your data. It doesn't tell you what you can do with your data. And when you want to ask that question, then you have to think about decision making. But again, our Bayesian framework gives us all the tools for that. And one of the tools that I like most is what we could call Bayesian policy search. And again, using that variational building blocks framework, again, we can build our models, do our inference, actually execute the policy, and do testing in one way. So if you wanted to build an algorithm to do reinforcement learning, for example, a simple way would be to build the following hierarchical model. It involves a prior with some latent variables. So you build a building block that just in TensorFlow just samples that distribution. A Gaussian, you build a distribution over actions. Again, you put a categorical distributions if you're in a discrete action space. And then you have an environment or a model. And typically, this is not something you can do, but you put your entire simulator. You put the DeepMind labyrinth environment or the OpenAI universe in that box. And you simulate forward, and you get the rewards that you think. And then inference, again, is the similar kind of building blocks. Everything that is unobserved, you just need to build a distribution over. Again, you sum up all the terms, and then automatic differentiation will do the rest. So this one I like quite a lot. It's an instance of a variational MDP, but we have many instances of such Bayesian approaches to doing decision-making. For example, planning as inference is one that I like quite a lot, or even KL control, which I think is great. So all of these approaches can be built together, and in this modular building block framework, and each of these blocks, for example, in the context of this workshop, can be a deep neural network, but that need not be the case. They could be kernel methods, non-parametric, semi-parametric models, etc. So these are all the tools we have. We have two different kinds of models, implicit models and prescribed models. We have different ways of doing inference for both kinds of classes. The principles of inference are either marginal likelihood or density, marginal density estimation, or hypothesis and two-sample testing. And then we have many different ways of actually doing decision-making and executing those actions. So I wanted to think about what we would do now to build an actual agent that, like us, can do a lot of different reasoning. So here's a few concrete tasks for a self-reliant agent. So the first one is that you might want to think about an agent that can reason about physics, objects, or scenes in some way. And with all the tools that we've described, I think we can do this, and we'll only get better at doing this over time. The second maybe concrete task is let's form conceptual understanding of the world, of our environments. If we can form this conceptual understanding, we can then, again, put them together in different ways and then do decision-making, exploration, and acting. Then we want to engage, I'm going to use this word future thinking, which I take from neuroscience and cognitive science. But this is a way of thinking about future outcomes in your model. What is the future evolution of the system you are studying? If it's an environment or a physical system that we're dealing with, we want to make predictions. We want to know future outcomes. We want to use the model to make counterfactual statements about the world. And finally, we actually might want to make those decisions, take those actions, and update our policies in some way. So I have 4 videos to show you about these kind of things, just to give you a taste, and then maybe together we'll build even better versions of these. So the first one, this video that I'm showing, is the classical example that you have in cognitive science of the Necker cube. And this is a generative model, a probabilistic model of the type that I showed you, over volumes and 3-dimensional objects. So again, the building blocks are very easy. We just need to put a prior, which is a Gaussian. We build another building block, which gives us an observation over volumes directly using a volumetric convolution in this case. And then we can do the posterior inference. And then in this case, we're doing this missing data completion to see what does our model learn. And you can see it first forms it, then it assesses how it should fit, and then rotates what's missing to readjust. And then we have the top bit that helps us understand the scene from different viewpoints. We can then rotate these 3-dimensional scenes within the simulation of our model, and then hopefully use that for understanding different viewpoints and ways of reasoning. And hopefully we'll be able to scale these these kind of tasks. So a second part of scene understanding is this one, the video play. So here's the video at the bottom is just a multi-MNIST set of images. And if you are a reasoning agent, there are some things you want to be able to do. You want to be able to know that there are a discrete number of objects, and you want to be able to count those number of objects in this video. You might also want to know that what the identity of these objects are, and you'll actually be able to generate alternative variations of these objects, and that's basically the learning process. Each box shows you that this model is actually being able to know how many images there are, where they are localized, and actually generate consistent variations of it. And then, of course, agents can operate in multiple different environments and three-dimensional scenes. So you need to be able to know where these objects are in the scene, be able to reconstruct them, and do alternative reasoning over these scenes. So the second part is sort of concept learning, and there's a lot to do with concept learning. This is the Atari game called Submarine Freeway. What is this one called? I forgot. Anyway, Sequest, yes. So the first one is the original video to just give you a form. And again, this is just a simple density model to show you what is possible when you want to look for factors of variation that actually separate things out. So here you can see one, we have things for the score, so only the score changes. One kind of concept for the oxygen bar, another kind of concept for going up and down, left and right, and the number of lives. And this is what we want an agent to be able to do, recognize that these kind of concepts and sets of meaning within the data that we'd see. Another aspect of concepts is when we see new data, can we rapidly learn from that data? And we have a very good example of another Bayesian way of dealing with that from Tenenbaum and Lake, which used the Bayesian probabilistic program. In this case, we use the Bayesian neural network to show that we can do strong generalization, that when we see new data for the first time that we have never trained on before, our model in some way understands the common structure, the underlying concepts related to these digits, and then can easily produce meaningful reproductions. So this is a task that could be called one-shot generalization. So then I mentioned this idea of future thinking. You'd like to have agents that, like us, can imagine how the future evolves, what are the other outcomes that happen, and then use their thinking to predict future rewards, find sub-goals, and solve tasks. And this is a video from the Labyrinth environment that was released open sourced on Monday. And it's a really nice environment to do lots of things to test these kind of future thinking that we actually want to have in our agents. And finally, you want to do some actions and planning. And this is an example of Pac-Man, Miss Pac-Man, on that variational MDP that I showed you. And this video goes a little bit further, that it tries to do hierarchical planning and do macro actions. So the middle row is the thing that you're actually interested in. That is the policy, and every row is one of the discrete actions. And this, the x-axis is time, and you can see it can generate future possible actions and then take these actions. And then Miss Pac-Man can actually solve things. And then because you actually, when you solve the variational method, you get a score function estimate, and you have to solve it by you get a policy gradient method, which is where the value function enters. So I spoke about these four parts: scene understanding, world simulation, visual concept learning, and macro actions and planning. But this is sort of just the beginning and all the time I have to tell you today. But I think there are many other things, and Bayesian reasoning will be the key to all of these parts. Data efficient learning will only become more important. The continuing problem of exploration in reinforcement learning, it's not enough to know that there are concepts, but there are multiple concepts that are related to each other, so relational learning will become important. We only look here in parametric models, but I'm a strong believer of, again, this integration of things. So we have non-parametric and parametric models, which we call semi-parametric models, which will come together. Of course, agents need to form hypotheses, do scientific experiments, if you like, and how we do this hypothesis formulation through Bayesian active learning will be one way. And of course, doing causal reasoning, where we can form long-term dependencies, look at the causal structure over long periods of time, will become important. So other concepts that you have seen, I think, throughout the conference, and I think are the key questions for us to now address, are evaluation of these models. No one can seem to agree how we actually evaluate our probabilistic models, because we usually don't have a very concrete task. But this will be one of the things we'll think about. Once we start building a system like this that can do world simulation, concept learning, and macro actions and planning, we need to put them together. So integration of different kinds of components, but deep learning and Bayesian methods make this kind of integration very easy. You've heard about the concept of memory, which is very popular in machine learning. Memory is something we have a lot to say about from Bayesian thinking, which we have not been doing so far, and I think we'll do more over time. Discrete modeling, and there's a lot of good posters here today that try to address this, and this will be important when we need to think about structure learning and how we have to adapt our systems as we gain more and more data and need to become more flexible at more tasks. And of course, building a continually learning agent system will be important. So I think there's a lot to do. This workshop was really great, and I think we'll just see more about Bayesian agents and the way we can bring together many more different fields of machine learning other than just Bayesian reasoning and deep learning, and hopefully we'll work together towards that. Thank you very much. Don't know if there's any questions.
So we have time for questions.
I know you didn't speak about this directly, but I'm curious about some of the decisions that were made in the in work on the data centers, optimizing efficiency in data centers, and how, if at all, you use kind of Bayesian techniques to mitigate kind of risk of deployment and basically like questions about like modeling the environment and these kinds of things.
Yeah. Unfortunately, I wasn't working on that project, so I can't say too much. But of course, I think there's a big role for modeling uncertainty in making those kind of decisions. But yeah.
Anyway.
Okay. Cool. Okay. Thank you.
Hi. So I'm wondering if you can say something about the interaction between decision theory and approximate inference. So if you're using your inferences to make decisions, then is the sort of standard variational KLQP, is that the right approximation that you want, or are there maybe other principles to?
Yeah, so I think, as I said, when you think about the reinforcement learning setting, then this variational approach actually fits very neatly into that setting. If you look at the planning of inference approach as well, the other way you think about this kind of decision making is through risk minimization. So what you then have to do is one more step further, where you actually have to think about the loss you are dealing with and then integrate the loss or compute the risk of the problem that you're doing. And this then gives you all the ingredients to actually go forward and complete that one more step. You might sometimes call that the loss calibrated Bayesian, and then you complete your full decision loop in that way. So yeah.
So a quick question about the relevance of Bayesian approach. There is a lot of deep learners who advocate for using ensembles from different random initialization points. There is a very recent paper by Charles, who was himself a Bayesian, and Balaji, who now say, well, we can use ensembles and we don't need Bayesian anymore, yet we can take into account uncertainty. What's your feeling about this?
Yeah, what shall I say about using
Sorry,
ensembles?
Shakir.
Well, as I said, pardon? Yeah, let's do this one in the discussion, actually, on the panel, yes. Okay, thank you. Is there more? Yes.
I didn't answer just to the, and it actually relates to both of the last two questions, but on the data center side, we actually use the non-parametric bootstrap. So that's subsampling your data. And then we use that as an uncertainty measure for the policy in the data center control. But it wasn't just an ensemble. It was an ensemble of bootstrap data set.
Okay, good. All righty.
We can thank the speaker again.